Hello, and we are going to continue our discussion on acids and bases. It is such an important topic that we are going to spend another video or two on it as we look at strong versus weak acids. What makes something a strong acid? What makes something a weak acid? That's what we're going to be asking ourselves today. So, maybe you've heard the idea that acids can burn, right? Some acids are safe to handle with your bare hands or even used in food preparation, but other acids may burn your skin. And so it's important to understand how these substances can all be acids and yet have very different properties. So let's look at Model 1 to help us understand. This Model 1 is trying to help us understand acid strength and conductivity. So I'm just going to mention here, remember, one of the definitions of an acid is that when you put it into water, you are going to have hydronium ions, which really, remember, is the H plus and the water. H plus and a water molecule put together. Oops, sorry about that. Those two are going to form your hydronium. That's an ion. Ion is a charged particle. Okay? So acid, when you put it into water, is going to form ions. It's true for a base as well, but we're going to focus on an acid right now. So here we are told that we have HCl, which is a strong acid, and we're going to see what is true about that acid. Here we have HF, we're told that's a weak acid, and we're going to compare the two. Excess water molecules in the solution are not shown, just so you know. They are showing water molecules, but obviously there's millions and millions of water molecules besides the ones that are shown. Examine the symbols in Model 1. Match each symbol with its correct meaning. So, a water molecule, an acid molecule, a conjugate base, or the hydronium ion. So let's see if we can make sense of this. Let's look at this reaction up here. HCl and water. So these are the HCl molecules. They're going to be put into water. So it looks like our HCl, our acid, whether it's HCl or HF, is represented by this diagram. Okay? Even though they look the same, this is HCl and this is HF, but the model is showing us that this is going to be our acid. Okay? Our water molecule is going to be this one. Looks like Mickey Mouse ears here. Okay? There's your water molecules in there. Then, when the H plus and the water get together, you're going to form hydronium ion. So that is this one here. It's basically the water and then another hydrogen added to it to give you the hydronium ion. And then this guy right here is the acid without its H. So it lost its H plus, and that we know is our conjugate base ion. So that is our C. Okay? And you'll see that those appear in the solution after you've added it to the solution. Okay? So these reactions are an acid put into water, creating hydronium and the conjugate base ion. An acid put into water, creating the hydronium and the conjugate base ion. Examine the strong and weak acid solutions in Model 1. What product do the solutions have in common? Well, they both are forming hydronium. Use a complete sentence to explain the formation of the product in Part A from an acid molecule and a water. So we're going to have H plus and the water going to form your hydronium. Okay, you can say that the H plus comes from your acid. The acid, whether it's HCl or the HF, they're going to donate the H plus to the water to form your hydronium. Assume that solutions of HCl and HF, that they're similar to those in Model 1, that they're prepared, and infinitesimally small samples are collected and analyzed to determine the amount of ionization that occurs. Based on the data below, calculate the percent ionization for each acid solution. Solution A has been completed for you. Well, before we get there, let me just point something out to you. You may have noticed this, you may not have noticed this, but if we look at this solution here as compared to this one, look how many more ions. Lots of ions. In this one, not as many ions are formed down here. So that's an indication on whether something is strong or whether it's a weak acid. If it forms lots of ions, if it breaks apart, if it dissociates completely, that's going to be a strong acid. If it only forms a few ions, in other words, it breaks apart just a little bit, not all of the HF molecules break apart into ions, then it's actually called a weak acid. But let's confirm that down here in our data. So if we have HCl and we have a 0.06 molar, remember this stands for molar, that's moles per liter, of HCl, the initial number of acid molecules is 40, and then the number of acid molecules that reacted, 40, and so we're going to write a ratio. Molecules that reacted over the initial molecules, 40 over 40, 100% of them created ions. 100% of the original HCl broke apart into H plus and Cl negative. And we know that H plus is going to react with water to form the hydronium. But I'm just simplifying it. Here, HF, 40 of them, but only 8 reacted. So how many reacted? 8 out of 40, and you can calculate the percentage right there for us. Okay? So it's 1/5 or 20% basically. Alright? 20, again, HCl, 20. Now this time we have fewer. Do you see how the concentration is less? Here we got 0.06, here we got 0.03. So we have fewer particles. It's not as concentrated, fewer moles per liter. But look again, all of them react 100%. Whereas here, if you got 20, only 4 of them, again, 4 out of 20 is going to be your 20%, or 1/5. Okay? So, as I mentioned before, when you looked at Model 1, you noticed that the HCl created a lot more ions. All of them broke apart into ions, whereas the HF, only some of these are going to break apart into ions. In other words, some of them are going to turn back into HF. That's why we're going to have a reversible reaction here, whereas HCl is only one direction. This is a complete ionization. Complete ionization. HF is only a partial ionization. This complete one we say is a strong acid, and this partial is called a weak acid. Okay? Electrolytes are substances that dissolve in water to produce ions, like our acids, like bases, all right, like or not any, but lots of ionic compounds. The presence of ions allows a solution to conduct an electrical current. Ions may be produced because the substance that dissolves is ionic, like salt, NaCl, for example. It's going to break apart into Na plus and Cl negative. Okay? Or because the substance reacts with water to produce ions, as is the case with acids, donates that proton. The more ions that are formed in solution, the stronger that electrolyte. Okay? Non-electrolytes are substances whose aqueous solutions do not contain ions and therefore do not conduct electrical current. So for example, sugar will dissolve in water because it's polar, but it doesn't create ions. It doesn't break apart into ions. So sugar water is not going to conduct electricity. Salt water will. Which solution in Model 1, the strong or weak acid, is a better conductor of electricity? Well, you will notice because of the light that is shining up here, this is a little instrument that has a light bulb on there, and when you put it, these probes, these little metal electric probes there, are going to then complete the circuit if you have charged particles in here. If you've got a lot of them, the brighter the light will be. If you only have a few particles in there that are charged, you're going to have a dim light, and this is an indication of how many ions you have in your solution. Okay? So the strong one has more electrolytes in there, has more ions. Based on the data and the table in question 3, describe the relationship between the percent ionization of the acid and the conductivity. So as the percent ionization goes up, so does the conductivity. That just tells you you've got more charged particles in there. Strong acid has complete ionization and therefore lots of ions. The conductivity of the solution and the strength of the electrolyte, basically same thing. Greater the conductivity, the stronger the acid, as I just mentioned up there. Consider the conductivity data shown in Model 1 and the ionization data in question 3. So we have Model 1 and question 3. Is HCl a strong acid or weak acid? It is a strong acid. And how do we know strong acid forms lots of ions? In fact, we say a strong acid has complete ionization. It completely ionizes. HF is your weak acid, and because it has a lesser percentage of ionization. Strong, 100%. All right? A weak acid is going to be less than 100% ionization. In many cases, much less than 100%. Does a change in concentration affect the strength of the acid? Use the information in question 3 to provide specific evidence. What they're saying is, it doesn't matter how many particles you have of HCl, all of them are going to ionize. You will always have 100% ionization for HCl. Doesn't matter how much you have of it. That's the point. So, HCl is always a strong acid. Doesn't matter if you have a little of it or a lot of those particles. 100% ionization indicates it is strong. Okay? All right. In one of the reactions in Model 1, there's a single arrow. In the other reaction, there's a double arrow. So single arrow means that you have a complete reaction. It goes only one way, one direction. Double means you have reversible. And that means it goes both ways, right? So you can have the reactants turning into products and the products turning back into reactants. Well, what does that tell you? Basically, it tells us that if you have a single arrow, you have a complete ionization. It's telling you the extent of the reaction, that all of the reactants are turning into products. Okay? The reversible one says only partial reaction occurred. Forward reaction went into action, it took place, but then the reverse reaction also kicks in, and so they counteract each other, and you don't have a complete reaction. Not all of your reactants are going to be used up. You're going to have some products formed, you're going to have still some reactants. Both are going to be in existence for reversible reaction. But for a single direction, complete one-way reaction, you're going to have reactants being consumed, products being formed, not going back the reverse direction. Okay? And if you see a single arrow, that means strong, because all of the acid is turning into ions. If you see reversible, that means weak acid. A solution of 4 molar, remember that's moles per liter, sulfuric acid is a stronger acid than 1 molar solution of sulfuric acid. This is what a student is saying. Construct a well thought out response to help the student improve his understanding. Well, when we say stronger acid, strength is a measurement of percent of ionization. That's how we're defining the strength of the acid. So H2SO4, if 100% of it ionizes, it doesn't matter if you've got 4 molar or 1 molar, it's always going to be 100% ionization, and so you don't, the strength of the acid is not determined by its concentration. The strength of the acid is determined by its percent ionization. In the beaker below, draw a representation to show 10 molecules in a weak acid dissolved in water with 20% ionization. Include only the water molecules that react, not the excess water molecules in the solution. So here's our molecular acid. This is your H and then some non-metal. So this could be like HF or something. The A here is just representing some general non-metal. It's not being specific. Okay, here's your water. There's your H2O. And we're going to take 10 of these, but only 20% of them are going to ionize, meaning that if they do ionize, you're going to create H plus and the A negative. Okay? Or specifically, this H plus probably is going to then join with water to make your hydronium, right? So, if you have 20% of them, that means 2. That's only 2. 2 of these 10 are going to break apart. So you're going to draw 8 of these together. Eight of them stay together. There's 8 right there. And only 2 of them are going to break apart. I'll put the other one up here. Alright, something like that. Oops, sorry, that should be a plus. And if you want to, you could turn the H plus into a hydronium here. Okay? There's your water molecule with the H plus. That's your hydronium. Another water molecule with your H plus. There's your hydronium. Alright? So there are the 2, this one and this one. Those are the only 2 that ionize. The others are still stuck together. That's because this is really a weak acid, and when some of them try to ionize, they actually resist that and they turn back into that acid, let's say HF for example. Okay? This is weak. Weak acid. Alright, you have conductivity meters in a 1 molar solution of, this is nitric acid and nitrous acid maybe. And there you have acetic acid. The 1 molar HNO3 light bulb is bright. The 1 molar HNO2 light bulb is giving off some light. And the 1 molar for the acetic is very dim. So again, we're just measuring the strength by using a light bulb to show the conductivity. More ions, if you have lots of ions, then your conductivity is going to be greater, and that tells us the strength of the acid is going to be greater as well. Okay? So you can do that. You can rank these. Obviously, we're going to rank the acid strength. The one with the bright bulb, the HNO3, nitric acid, that is your strong one. And then a little bit of light, that is your nitrous acid, that is a little bit weaker. And the weakest is your acetic acid, it's very dim. Okay? Based on your answer in question 11, write balanced chemical equations for all for, oh, these two. We're just going to compare these two. Reacting with water as they are mixed into aqueous solution. Use single or double arrows. Okay, this one was strong, meaning we're going to show 100% ionization. This one was weak, which means we have to show that not all of it ionizes, and we use the double arrow to indicate that. So HNO3 compared to HNO2, single arrow, complete ionization. And I'm going to put the water like this. Instead of plus water, there's another way to show this, is by just putting the water above your arrows. But that means that this is going into an aqueous solution, so we have water to react with. So you're going to form hydronium ion and the conjugate base anion. And here you're going to form, yes, you're going to form hydronium ion and HO2 negative, but this double arrow tells me I'm not going to have very many ions in this second reaction right there. Okay? Strong, weak. Our extension questions today, we're going to be looking at something called equilibrium constant expression. So as mentioned in a previous video when we talked about equilibrium, equilibrium happens when you have a reversible reaction and you have the forward direction of the reaction occurring, the reverse direction occurring, and over time you're going to have both directions happening at the same rate. It doesn't mean you're going to have the same number of products and the same number of reactants. It doesn't mean the quantities are the same. It just means the two directions are happening at the same rate. Every time you have reactants turning into products, you're going to have the same amount of products turning back into reactants when you have reached equilibrium. That happens when you have reached equilibrium. Okay? Up until then, the two directions are not at the same rate, but they'll keep working back and forth until they balance each other out, and they'll continue to react even once they've reached equilibrium. It doesn't stop, but now the two directions are equal, and you're going to have a state of equilibrium. The numbers are not going to change drastically. The numbers are not going to be the same. That's not what I'm saying. Okay, I repeat that. But the numbers are not going to change once you've reached equilibrium. So here we have an equilibrium constant expression, and let's figure out what this means for us. Here we have a general reversible reaction for a generic acid, HA. A represents any non-metal that would form an acid. Reacting with water, creating hydronium and that conjugate base ion, anion. And then we have an expression right here. We have a K, that's going to be the letter that we use. The subscript here is A for acid. And you'll notice what we have here is we've got the products, hydronium ion and the A negative, the anion, are in the numerator, and the the reactant HA is in the denominator. We're going to leave out the water because it's a pure liquid. And these brackets here, when you put something, you put a formula in bracket, it means concentration. Okay? Concentration, concentration. So anything in brackets means we're measuring the concentration of that, like molarity, molar. Okay, that's what that means. In Model 2, does HA represent a weak acid or strong acid? Ah, right there. Reversible reaction, I know it's weak. Done. Compare the equation above that starts out K equals to other equilibrium constant expressions you have seen. Well, we've got an A here. Is Ka calculated in the same manner as other KEQ values? Yes. We're going to put products in the numerator and reactants in the denominator. Okay? What molecule in the reaction has been left out? We did not include water. Why? Because you don't put pure liquids, or for that matter, you don't put solids into equilibrium constant expression because their concentrations don't change. We're looking for things whose concentration change. And a solution, an aqueous solution, can have more particles or less particles of the solute, so its concentration can change. Okay? Consider what you learned in Model 1 about the extent to which weak acids react with water. Is the value of Ka for a weak acid likely to be greater than or less than 1? Explain your answer in terms of the numbers that might be used in the equation in Model 2. So here's what we're saying. If our K expression is reactants over, products over reactants, if you have a lot of product and little reactant, lots of products, little amount of reactants, then K is going to be large. When does that happen? When you create a lot of ions. For acids, if you create a lot of ions, that happens when you have a strong acid. It completely ionizes. So that means this top number is going to be large for a strong acid. So Ka is large when you have a strong acid. Ka is small. By small I would mean, less than 1, even a lot less than 1, for a weak acid. All right? For a strong acid, it's going to be greater than 1. Okay? As explained right here. Just look at the numerator and denominator. If the K expression is products over reactants, and if your products are the ions, if you got lots of ions, this top number is going to be big, the bottom number is going to be small. That is a large value for strong acids. If it's a weak acid, you don't form very many ions. So the top number is going to be small, the bottom number is going to be big. You're still going to have a lot of that reactant still there in solution. It's not going to break apart. And you're going to have a small value for weak acids. All right, consider the weak acid, ammonium, NH4+. Write the acid dissociation reaction for NH4+ using Model 1 as your guide. Pay close attention to the arrow, single or double, that you should use. And then we're going to write the Ka expression. All right? So, the acid dissociation reaction for this. If this is going to behave like an acid when you put it into water, then what's going to happen here? It is going to donate its H+, and it's going to form hydronium ion, and it's going to give up one of its H pluses and become NH3. It's given up the plus, so it's going to drop by, the charge is going to drop by 1, so it's going to become NH3. Okay? And this is a reversible reaction because we were told it's a weak acid. The NH4+ is donating the H+, so we have shown that by our products here, and it is acting as an acid. The water is your base. Over here on the other side, the ammonium ion turns into ammonia, so this is your conjugate base. The water in this case is acting as a base, and it is turning into hydronium, which is your conjugate acid. Okay? Okay, write the Ka expression. Well, the Ka expression then would be this. Remember, we don't put pure water, we don't put pure liquids into the Ka expression, into the equilibrium constant expression. So you would have concentration of hydronium ion times the concentration of the ammonia at equilibrium divided by the concentration of the ammonium ion at equilibrium, and that would be the Ka value for the weak acid ammonium ion. Okay? All right. So, strong and weak acids, it's all about the percent of ionization. Strong acids completely ionize, weak acids do not. And we're going to continue talking about acids and bases and look at something called pH. We'll see you in the next video.